So we were dealing with molar conductivity. What is the variation of molar conductivity with consumption? Molar conductivity, that is lambda m. Specific conductivity, that is the conductivity. Conductivity is also called specific conductivity. Similarly, resistivity is also called specific resistance. A specific resistance, that is also. This is conductivity, a specific conductance. Conductivity, and this one is molar conductivity, lambda molar conductivity. What is the variation of conductivity with the dilution? What is the conductivity of what is the variation in molar conductivity with the dilution? Molar conductivity lambda m, you know, it is kappa into thousands upon molarity. You can calculate molarity from this. Molarity means solubility. We can talk molarity as solubility. Solubility we talk in the terms of sparingly soluble. What is molar conductivity? Again, we are coming to the definition of molar conductivity. Molar conductivity is the conductance of 1 mole of an electrolytic solution. 1 mole of an electrolytic solution. Conductance of an electrolytic solution kept between electrodes at unit distance. So this is unit distance. Electrodes at unit distance. Electrode conductivity set and keeping it vertical. You will see like this. Like this. Okay, this is the connection wires. Connection wires you can connect in any way. Solution you cannot connect directly, so we are using this conductivity set. And passing AC, passing DC will change the consumption, so we will be using an AC. Now this conductivity cell contains 2 electrons. They are kept at unit distance. Unit distance. So it is the conductance of an electrolytic solution. Conductance. You know that R is equal to rho L by A. Inverse 1 by R is equal to 1 by rho into A by A. What is 1 by R? That is the conductance G. Conductance G, which is equal to kappa 1 by rho is kappa into A by L. Now we are keeping a unit distance. Unit distance, and you are diluting this. We were saying the variation of molar conductivity with the dilution. You are diluting this. You are diluting this means the molarity or the concentration decreases, but you have to catch hold of 1 mole. 1 mole of electrolyte in this confined volume. Volume I say because it is a unit distance. But you have to catch hold of that 1 mole of electrolyte. So that you have to increase the area of cross section. This should be unit distance. There is no change in that. How can you catch hold of that 1 mole of electrolyte? By increasing the area of cross section. Suppose these are the two electrodes. I am keeping these electrodes here at the unit distance. Now, between them, some solution is confined. We are looking at the solution. Now we diluted that. Diluted means after dilution, you have to catch hold of 1 mole of that, what you have to do, you have to increase the area of cross section. Increase the area of cross section means now I have increased the area of cross section. First I used these two. I kept like this. I kept like this. Then now I have increased the area of cross section. Increase the area of cross section means, see, now the size is this much. Now the size is this much. Now I am keeping this like this. Now I have to consider 1 mole of an electrolytic solution. See, I have increased the area of cross section so that I can catch hold of 1 mole of electrolyte between these two electrodes. So molar conductivity is the conductance of an electrolytic solution. Length is same, that is unit distance. Now G is equal to, what is changing? This A. Since length is unit distance, then this will be what? Volume. This will be volume. I can write like this, kappa into V. So molar conductivity is the conductance, and this is called molar. It is the molar conductivity. It is the molar conductivity is the conductance of an electrolytic solution kept between two electrodes at a unit distance, but having an area of cross section large enough, see, large enough to accommodate 1 mole of an electrolyte, to accommodate sufficient volume, that is big enough, large enough to accommodate 1 mole of electrolyte. So what is the definition? Molar conductivity is the conductance of an electrolytic solution kept between electrodes at unit distance, but having an area of cross section large enough to accommodate, sufficient volume that contains 1 mole of electrolyte. Ultimately, it is the conductance of 1 mole of electrolyte. 1 mole of an electrolytic solution containing 1 mole of electrolyte. So lambda n is also given by kappa into V. As V increases, of course, on dilution and dilution, to catch hold of that 1 mole of electrolyte, area of cross section will be increasing. That means volume will be increasing. So on dilution, volume increases, so molar conductivity increases. Molar conductivity increases on dilution. Molar conductivity is the conductance of an electrolytic solution kept between electrodes at unit distance. Molar conductivity is the conductance of an electrolytic solution kept between unit distance. Electrodes kept at unit distance. There is a conductance of an electrolytic solution kept between electrodes at unit distance. So electrodes at unit distance means these are the electrodes. These are the electrodes. In the beginning, we took these are the electrodes. In between this, it was highly concentrated, means between these two electrodes, 1 mole of electrolyte is confined. So 1 mole of electrolyte we have between these two electrodes. Now, on dilution, one mole of electrolyte will not be there. You added water, one mole of electrolyte will not be there. So what we did to catch hold of that, we increase the area of cross-section. Instead of that small electrodes, now we are using this electrodes, these electrodes. So we have increased the area of cross-section. Area cross-section. Okay. So lambda m is equal to kappa into V. Of course, on dilution, kappa will be decreasing. That you saw yesterday. On dilution, this kappa, that is this conductivity, will be decreasing. Conductivity decreasing means we are considering the 1 cc of the electrolytic solution. So on dilution, what happens? The number of ions in this will be decreasing. So conductivity will be decreasing. Again, after dilution also we are checking the conductivity of that 1 cc, conductance of that 1 cc of the solution. So here lambda m is equal to Vk. On dilution, kappa will be decreasing, but this decrease is more than compensated by this increase in volume. So ultimately, on dilution, lambda m is increasing. If you draw a graph for strong and weak electrolytes, conductivity for strong and weak electrolyte. Strong electrolyte means KCl or NaCl. Weak electrolyte means CH3, COOH. Weak electrolyte. Conductivity will be decreasing. On dilution, the conductivity will be decreasing. What about the molar conductivity? Strong and weak electrolyte. Strong and weak electrolyte. In the case of strong electrolytes, in the case of strong electrolyte, I'm going to plot a graph between the concentration, not exactly concentration, and a proper graph is obtained when we mark root C against lambda m. This is for strong and root C against lambda m. In the case of strong electrolyte, this is the graph. A straight line, you can extrapolate the graph. And here, in the case of acetic acid, strong electrolyte KCl, weak electrolyte acetic acid, HCl, H3PO3, H2CO3. These are weak electrolytes. H2CO3 or CH3, COOH, HCl, HF. Okay. In the case of weak electrolytes, conductivity slowly increasing. Yes, weak electrolyte dissociates very slowly. Weak electrolyte dissociate very slowly. That is why we are calling them weak electrolyte. A weak electrolyte dissociates very slowly. So ions, the production of ions, number of ions will be getting slowly. So slowly the number of ions are increasing slowly, very slowly. It is increasing. I am drawing from that side because there it is higher concentration. Here it is lower concentration. Lower concentration. Actually, we are dilating it, so we have to come towards the lower concentration. From higher concentration to lower concentration, slowly, very slowly, it is increasing slowly. And as we come to this concentration where it approaches zero, when the concentration approaches zero, friends, when the concentration approaches zero, its water conductivity sharply increases and it goes parallel to the y-axis. Parallel to this y-axis. Why it is so? Towards this infinite dilution, the degree of dissociation increases. And when it approaches zero, the degree of dissociation alpha is equal to 1. That time our acetic acid behaves as a strong electrolyte. So its molar conductivity increases steeply and it goes parallel to y-axis. Why it is increasing? Because degree of dissociation is increasing. Here also degree of dissociation is increasing. Degree of dissociation. When it approaches zero concentration, that means infinite dilution. Infinite dilution. Complete dissociation. That means CS3COH will be acting as a strong electrolyte. Alpha is equal to 1. So its molar conductivity steeply it increases and it goes parallel to y-axis. Now, when you extrapolate this graph means towards infinite dilution, it's all diluting and diluting. When the concentration approaches zero, that time lambda m is called lambda naught m. On dilution and dilution, when the concentration approaches zero, that time lambda m is called lambda naught m. So I'm extrapolating this graph to get that lambda m at infinite dilution, which is called lambda naught m. On extrapolating the graph, that means when on dilution and dilution, when the concentration approaches zero, lambda m is called lambda naught m. This is called limiting molar conductivity. This is called lambda naught m is called limiting molar conductivity. In the same way, by extrapolating the graph, you will not be able to get this lambda naught m because this graph is going parallel to y-axis. It will not touch y-axis. So, by experimental method, you will not be able to get lambda naught m in the case of acetic acid, a weak electrolyte. Then, what can we get? Okay, before that, this lambda m is equal, this is straight line, lambda m is equal to, for straight line equation, lambda naught m minus a into root c. This equation is called Debye-Huckel-Hunsaker equation, which is not free. Equation is there, the name of the equation is not free. So lambda m is equal to lambda of straight line minus a is a constant into this root c, under root c. A is a constant for a particular type of electrolyte. We call it as, we categorize the electrolyte as 1,1 electrolyte, 2,1 electrolyte, 2,2 electrolyte. What is 1,1 electrolyte? We categorize the electrolyte in different categories. That is NaCl, based on the valencies. Valency of sodium is 1, valency of chlorine is 1. Then MgCl, balance. So this is a 1,1 electrolyte. For this type of electrolyte, there is this A is a constant. A can be particular value. Now for MgCl, the valency is 2, yet the valency is 1. So this type of electrolytes are called 2,1 electrolyte. And next is MgSO4, 2, 2. So these types of electrolytes are called 2,2 electrolytes. For those type of electrolytes, there is a special value for A. Okay, that's about that A. So this equation is a straight line and this equation is for strong electrolyte. And now, once you dilute the strong electrolyte means 100% ionization. When you make a solution with strong electrolyte, the number of all ions, all KCl got dissociated into K plus and Cl minus. And on dilution, no more ions are produced, no extra ions are produced, still the molar conductivity is increasing slightly. Molar conductivity is increasing slightly. In this case, as you dilute and dilute and dilute, degree of dissociation is increasing. So more and more CH3 or CH3COH is dissociating. So more and more CH3CO minus and H plus are produced. So more and more number of ions are produced means polar conductivity is increasing. But in this case, when you made the solution, 100% ionization. Now no KCl is there to ionize again. No KCl is remaining like CH3COH, like CH3COOH. KCl is there to ionize. Then how can this increase? On dilution. On dilution, the interionic interaction between K plus and Cl minus ions decreasing. That means they are more free to carry current. They are more free to move. So, polar conductivity slightly increases. When you add water, first when you made the solution, 100% ionization. All KCl got dissociated into K plus and Cl minus ion. So many K plus ions, so many Cl minus ions, all are dissociated, 100% dissociation. Now, when you add, no new ions are formed. No new ions are formed. Still, molar conductivity increases because when you add water, ions are separated. They are free to move. They are otherwise K plus separated K plus will be attracting Cl minus. So that interionic interaction decreased. So lambda M is increasing. That slide increase. For every strong electrolyte, you will be getting similar graph. Similar graph. What is lambda naught? Lambda naught M is the molar conductivity at infinite dilution. Means on dilution and dilution, when the concentration approaches zero, lambda M is called lambda naught M. What is limiting molar conductivity? Anybody?
Molar conductivity when concentration is zero.
On dilution and dilution when the concentration approaches zero, the molar conductivity at that point is called limiting molar conductivity.
Definition should be proper. Okay, you may think that, okay, I have written correctly. But examiner is a human being. He or she may not be liking the way of presentation of your answer. Accordingly, एक mark क्या क्वेश्चन है? They will put half mark. ऐसे 10 half mark कम हो गया तो गया. Okay. I thought video on करके admit करके सब लोग चला गया. Okay, Kondrashu made some observations. He studied the graph of the smaller conductivity against concentration of many electrons. And he concluded, he had a conclusion from his observation. For example, for KCl, we got a graph like this. This is for KCl. For NaCl also, we got a graph like this. So, when he took this lambda naught m of KCl and lambda naught m of NaCl, he found that lambda naught m of KCl minus lambda naught m of NaCl got value as 20.2 as centimeter square mole inverse. This he observed. He got an observation like this. So he took some other electrolyte, KBr and NABr. And then he subtracted that NABr, lambda naught m of NABr from KBr. He got again the same value. Is it by chance? So he took for Ki and NaI. Ki and NaI. So again for Ki and NaI. Again we got 23.4 as centimeter square mole inverse. So when he got like this, he made a conclusion. What conclusion he made? Since this is 23.4, 23.4, 23.4, left hand side also should be the same. Left hand side should also be the same. What can be the left hand side? What can be the left hand side? He said it is actually K minus Na, CL protects K minus Na, K minus Na, I protects Br protects. That means he said you can split this into individual contribution. You can split this into individual contribution. How? Lambda naught m KCl can be written as lambda naught m K plus and lambda naught m Cl minus. Similarly, lambda naught m NaCl can be written as an individual contribution lambda naught m Na plus and lambda naught m Cl minus. Now, for individual contribution, you have to write that small lambda like this. Similarly, in the three other two equations also you can write. So lambda naught m Cl minus and this lambda naught m Cl minus will get cancelled. That's how we are getting 23.4. So he made a law called the Kuldrash law of independent migration. Thank you. That we'll be doing next.